Okay, so in this video, we are going to go over properties of exponents, which should be a review for students in my class. But I'm dealing basically with integer exponents or exponents that are positive or negative whole numbers. That's what an integer is. So the first couple of rules, properties of exponent rules that I'm going to use is the product rule. So the product rule basically states that if you have something to the m power times that same something, a value to the nth power, as long as the bases are the same, so note that these have to be the same base, then you will get, when you simplify this, you add the exponents. So this is basically the rule. And also notice that the base does not change. So when we have numbers here, sometimes the students want to multiply the bases together. You do not multiply the bases together. The base stays the same. So here's an example of why this works. So let's say, for example, you have you have 2 to the third power times 2 to the fourth power. So 2 to the third power means 2 times 2 times 2. 2 to the fourth power means that you're multiplying 4 2's together. So if you count the number of 2's that you are multiplying together now, you have 1, 2, 3, 4, 5, 6, 7. So that's why when we simplify, we get 2 to the set, or when we are applying this rule, you add the exponents, 3 plus 4, and you get 2 to the 7th. But notice the 2 did not change. So the base stays the same. You just simply add the exponents. So let's do another example. We'll call this example A. And let's say you have something like 7 to the 6th power times 7 to the negative third power. So rather than writing it all out like we did with the 2's, we can simply, since we know this rule, apply the rule and simply add the 6 and the negative 3 together. So if you're adding 6 and negative 3, you get 7 to the third power. All right, so in this lesson for right now, we have not been exposed to the negative exponent rule. So I'm not going to apply that negative exponent rule yet. I will in a little bit. But so let's do another example, example B. But you're told to leave your answer in the form b to the nth power. So disregarding whether that exponent is positive or negative, we are not going to apply the negative. So do not apply the negative exponent rule yet. Okay, so we're just kind of playing around with this first rule, the product rule. So, and this time we're going to use a variable. So let's say we have c to the negative 10th power times c to the negative third power. So notice sometimes when you're multiplying, you have the dot in between. Sometimes you use parentheses. It really doesn't matter how you set it up. The base here, again, is the same. Your c's have the same base, but you have different exponents. Even if you had the same exponent, you would add the exponents. So you're taking c to the negative 10th plus negative third power. So when I'm adding those exponents together, I get c to the negative 13th power. And because the directions had said to leave the answer in the form of b to the nth power, I am not going to do not apply the negative exponent rule. So I'm just going to leave my answer as c to the negative 13th until I'm introduced to that rule and I apply that rule. So for right now, it's just we're getting used to using that product rule, which again means that when you have the same base and you are multiplying, the exponents get added, but the base stays the same. Okay, so now let's look at the quotient rule. So the quotient rule is what you use when you are dividing. So your quotient rule basically says this, that if you have a to the m power over a to the n power, instead of adding, you subtract. So when you're dividing, you actually subtract the exponents, the top minus the bottom. So the exponent on the top minus the exponent on the bottom. So again, doing a couple examples here. Example A, if I have the number 3 to the 4th power divided by 3 to the negative 11th power, it will equal 3 to the 4th minus a negative 11. So be careful when you have a negative exponent in the denominator. If you're subtracting a negative, that becomes positive. So we end up getting 3 to the 15th power. So be careful with those signs. So another example, using a variable. Let's say you have x to the 6th power over x to the 12th power. You would have, using the quotient rule, you would subtract the exponent in the numerator, which is 6, minus the exponent in the denominator, which is 12, and you get x to the negative 6. So again, for right now, we're going to leave it as x to the negative 6th power. So do not apply the negative exponent rule yet. And again, it's because in the directions for some of your problems, it says to leave the answer in the form b to the nth power. So if we were to apply the negative exponent rule, we would have to rewrite this as 1 over x to the 6th power, which I know some of you already know that, but for right now, just leave your answer in this form because we're just applying and practicing using this quotient rule. Okay, so the next examples, I'm going to apply several rules. I'm going to bring up several rules right now. So we are going to introduce the negative exponent rule and the zero exponent rule. So the negative exponent rule, actually I'm going to say negative exponent rules because there are a few different ones that I like to show, and that starting one is a to the negative n power. So if you have a base with a negative exponent, it does not mean that you have a negative number, which is the biggest misconception. When you simplify using the negative exponent rule, you rewrite this as 1 over a to the nth power. So you're putting 1 over the a to the n, but notice the exponent becomes positive once you move it down. Okay, so that's one of the negative exponent rules. So if I were to take this x to the negative 6th power here, using that negative exponent rule, it would be 1 over x to the 6th. So if you have to apply the negative exponent rule to this, you would rewrite this as 1 over x to the 6th power. Another negative exponent rule is when you have a negative exponent in the denominator rather than in the numerator. So if you have a negative exponent in the denominator, to make that negative exponent positive, again, you basically kind of take the reciprocal of this. So it would be a to the nth power over 1, which if you're dividing by 1, you don't really have to have that 1 in the denominator. But notice again, the exponent becomes positive. So if you have a negative exponent in the numerator or a negative exponent of something that doesn't have, if that's not in a fraction, then it goes to the denominator. If you have a negative exponent in the denominator, then you want to move it to the numerator and it becomes positive. So again, notice that negative exponent becomes positive. And then there's one other negative exponent rule that I like to show, and that's when you have a fraction. So when you have a fraction to a negative exponent, you could distribute the negative exponent to both and then move them from the top to the bottom. But what you end up with is the reciprocal of that fraction. So if you take the reciprocal of the fraction inside the parentheses, then the negative exponent becomes positive. And again, I'll show an example kind of like that, or why that works. Or actually, I'll do that right here. So if you have a over b to the negative nth power, and you distributed this exponent, which we haven't talked about that rule yet, but you're probably familiar with this one. If you had a to the negative n over b to the negative n, so the a is in the to the negative nth power is in the numerator. So if we move it to the denominator, the exponent will become positive. Your b to the negative nth power is in the denominator, so to make it positive, its exponent positive, we move it to the numerator. So, and this here, this statement here is equivalent to b over a to the nth power. So these are the same thing. These are equivalent expressions. All right, so let's do some more examples using, well, no, I've got a couple more rules to bring up. All right, so these are your negative exponent rules. Another rule that we use quite a bit is the power of a power rule. So basically this power of a power rule says that if you have anything to the m power taken to the nth power, so you basically have an exponent outside of an exponent, those exponents get multiplied. So this is your power of a power rule. And to show you a quick example of why that works, let's just say you have 3 to the 2nd power taken to the 4th power. So the exponent of 4 means that I have 3 squared being multiplied by itself 4 times. So this would be 3 squared times 3 squared times 3 squared times 3 squared. So 3 squared to the 4th power means 3 squared times 3 squared times 3 squared times 3 squared. Well, each of these 3 squareds represent 2 3's being multiplied together. So now if we count the numbers of 3's that we're multiplying together, of course the parentheses are not necessary, you would have 1, 2, 3, 4, 5, 6, 7, 8, or 3 to the 8th power. So again, you can see that if you simply multiply those exponents together, you will get 3 to the 8th power. So that's just a little quick example of why that power of a power works. Okay, there is another rule, power of a product. And I will be showing some examples of all these things in just a minute. So a power of a product, the rule basically says if you have two things being multiplied together, it could be a number and a variable or two variables, and you've got an exponent out on the outside, that exponent basically gets distributed to both of the bases. So the A and the B are both different bases, so that exponent gets distributed to both. Now keep in mind that these have to be multiplied together. So the A and the B are things that are being multiplied. You cannot have a plus or a minus sign in between here. Okay, so that is the rule that we're used to seeing. And then the other inverse of this, we also will use at times where if you have two different bases that have the same exponent, it may be beneficial for you to multiply those bases together and take it to that power. So as long as these exponents are the same and you're multiplying, you can multiply the bases together and take that whole thing to the power. So to show a couple quick examples of this rule and this rule, let's say you have 4x to the 4th power taken to the negative 8th power. If we distribute the exponent, you would have 4 to the negative 8th power times x to the 4th power taken to the negative 8th power. So then if we multiply our exponents together, so now we have our power of a power rule, the negative 8 and 4, we have two exponents there. So we would have a to the negative 8th times x to the negative 32nd. And then last but not least, now we're going to apply the negative exponent rule, because when you're simplifying exponents, your simplified answer should not have any negative exponents in it. Since both the 4 and the x have negative exponents, they will both go in the denominator, meaning we have to have a 1 in the numerator. Oops. So it would be, your final answer would be 1 over 4 to the 8th x to the 32nd. Now, 4 to the 8th is a pretty big number. If we had something like 2 to the 3rd down here, you might have need to simplify that to 8. But for right now, we're just practicing playing around with these exponent rules. So that would be your simplified form. And then I do want to show an example, a quick example of this down here. Try to squeeze this in. So let's say you have something like 8 to the 7th power times 3 to the 7th power. Well, because the 8 and the 3 both have an exponent of 7, you can multiply the 8 and 3 together and then write that to the 7th power. So 8 times 3 then would be 24 to the 7th power. So that's just an example of using the rule kind of backwards. But that is an important process also. Okay,